Thanks very much for organizing this workshop. It's a great pleasure to be here. I slightly changed the content of the talk, but the title is still okay. So we are 54 years after the algebraic eigenvalue problem. We just heard that. We are 58 years after the Francis QR algorithm. We are 68 years after the Arnoldi method, 69 years after the Lanczos method, and I could go on. How long ago? Is there anything to do in eigenvalue problems? So, we just need the software by Jack, and that will solve all the problems. So we have powerful computers, not like Jim Wilkinson in this picture, and we have fantastic software packages like nla-pack, scalar-pack, MATLAB, Python versions, and so on. Do we need any more research in this topic? Do we need better methods? Do we need more understanding? And can we do the backward and the perturbation analysis? Are there any structures that we cannot do? Or is it just enough to go back to Blackboard? It's my favorite photo of Jim, whom I only met twice in my life, unfortunately. What do you want to say?
That's all right. I'll tell you after.
Yeah. And the question is, are we following the Wilkinson heritage in the right way? And I will give you two real-world problems. And essentially, the talk will be all about questions and very little about answers. So the first one is a sexy title, Adiabatic quantum computing. You could also say solving large-scale eigenvalue problems. So this is was a project together with my colleague from theoretical physics, Tobias Brandes, who unfortunately passed away with 42 2 years ago, and the project has stalled a little bit. So you have the Schrödinger equation, and it's extremely large, discretized. So we're talking about 2 to the 1,000. 2 to the 1,000. And so the question is, can we do eigenvalue computations if we cannot even store a single vector? Either do it in limited memory or store them in a different way. And can we do an error analysis if we do eigenvalue computations with vectors that we cannot store? And then this was implemented in parts for classical and some non-classical models. So why are people interested, and why is this in adiabatic quantum computing? Essentially, if you want to solve NP-hard problems, you encode your question of factoring polynomials, factoring primes or things like that. You encode that with 2 to the number of bits elements, and you put that into a Hamiltonian, which is put together as a sum of a lot of so-called Pauli matrices, 2 by 2 matrices, which interact with each other. And adiabatic quantum computing means you start with a Hamiltonian where you know all the eigenvalues, and then you slowly move your problem into the problem where you want to know all the eigenvalues. And so you look at the ground state and the basic eigenvalues of that problem, and you look at how they move and see where they're going, and then at the end you take the eigenvectors of these eigenvalues and encode and decode your problem in the eigenvector basis associated with the ground states. So this is the time-dependent Schrödinger equation, and the trick is that you implement a Hamiltonian, so this matrix, in a tensor format. You don't implement it as a matrix. The first open question is, and then you compute the eigenvectors also in that tensor format. The first open question is, are the eigenvectors implementable in that tensor format? But you can try, but it's not clear. And the second thing is, can we follow the invariant subspace associated with the smallest energy levels if this dimension is extremely large?
How big is M?
The big M is essentially the number of bits that you're talking about. 2 to the 1000.
Okay.
Volker, you're not speaking of quantum computing, but of solving problems of quantum mechanics, right?
No, it's really, this is what would be used in adiabatic quantum computing.
You really mean that? Okay.
So it's actually, you let a molecule do that for you,
Okay.
but to code and decode, you would have to put it into the eigenvalue problem and the basis. And so this is a simple problem. You look at the eigenvalues. These are the energy levels of the molecule. You look at the eigenvalues. That's the ground state, and then the second, third, and fourth level. These are the lowest 15 eigenvalues for such an adiabatic. And they're moving from 0 to 1. And you want to follow and capture the eigenspace to the lowest eigenvalues. And this is the differential equation solved for the Schrödinger equation. And you see that here's one that jumps from one level to the other. And that's what you want to capture. And then in quantum mechanics, you have several effects. So this is one model. It's called the Adiabatic Grover Hamiltonian. And at a critical value 1/2, you can see here that it looks like the eigenvalues are crossing, but they really don't, except if you let n go to infinity, which you cannot. And so they are really avoiding each other. It's a well-known fact, but Peter Lax's book on linear algebra has crossing avoidance on the title of on the front page of the book. And the second one is a 1D Ising model. And you also see that eigenvalues are coming very close together. And we all know when eigenvalues are coming close together, we've heard this morning, then trouble is ahead. And the question is, can we still do the computations? And what are the difficulties? The first derivative of the ground state becomes non-analytic at this point. So whether it comes in like this or it crosses, unclear. And the second thing is, in the second example, the second derivative of the ground state becomes non-analytic. So what are the challenges? So you want to trace the smallest eigenvalue of an extremely large matrix. Symmetric, the good case, or Hermitian.
Not complex symmetric.
No, complex Hermitian.
Yeah.
The eigenvalue crossings are only visible in the higher order perturbation terms. So our classical perturbation analysis will not necessarily give you the information. At the crossings or near crossings, we all know there's a whole subspace that the eigenvectors can take. You only need a partial spectrum or an invariant subspace, so only the lowest level energy levels. But they may change the dimension, as you saw when they come close to each other. So you may follow a few ones, and then you follow more, and then you follow less, a few ones. And as we also know that Lanczos and Arnoldi and these methods don't do very well near multiple eigenvalues, even if the matrix is symmetric. And question what is if the problem is too large to run Lanczos or Arnoldi. And so the question is, can we run it into a truncated tensor format or in inexact operations, like Jack just mentioned that you could run it with 16-bit. That may be one way to get a little bit further. And we also want adaptive step size control to find these points where things come close. The second problem is a problem that I've been working for a long time. It's with the car industry. It's about brake squeal. So if you have a disc brake in a car, this problem is moving, and at certain frequencies after a certain years that you have this car, it starts to make funny noises. This is annoying. not only for you, but also for the people around. It's important for customer satisfaction, in particular in the German car producers, because customers don't get angry if you pay a lot for a car and it makes funny noises. It's a nonlinear effect. It's very hard to detect. And the car industry is trying for decades to improve this by changing the design of the discs and the brake. And so we had, for the last 6 years, we had projects. The first one was supported by the Ministry of Economics. You can imagine why the German car industry got this. Currently, we have a project together with one car company. Don't look at it. You can figure it out. This is a shim. A shim is a thing that is glued on the side of the brake. It's extra damping material. And what it's supposed to do is you optimize the damping material in order to minimize the effect of this squeal. So there are some colleagues who do experimental stuff with this. We put the shim into the finite element model, and we do stability and bifurcation analysis for this problem. So it's essentially, from the point of view of mathematics, the same question. When do eigenvalues come together? In this case, on the imaginary axis. When do they come together? And then you want to optimize that device.
If you eventually figure out how to do it, will you stop getting money?
No, I don't think so. So here's the problem. It's a linear eigenvalue problem, but with a parameter. And why it's a linear eigenvalue problem? Because they're doing linear stability analysis, finite element analysis. So the eigenvalue problem is a parametric. There's parameters in the coefficients which are material parameters, but let's not look at these. The most important point at the moment is this omega, and omega r is a reference frequency. That's the rotation speed of the disk. So at what rotation speed will the bifurcation set in? Will an eigenvalue cross the imaginary axis? And where does it cross the imaginary axis? And the matrix, the second order eigenvalue problem, this is one of the homes of polynomial eigenvalue problem. It's a difficult problem, in particular if you have to run it for 1,000,000 by 1,000,000 matrices and lots of parameters and all the time, and you have to figure out where the eigenvalues are. And it's pretty non-symmetric. And I will come back to this structure a little bit later. So what do? You make an ansatz, as we learned in the first course on differential equation, and you get a polynomial eigenvalue problem. And it's in one parameter. Non-linear in the parameter, but linear second order in the problem. And the likelihood of the break to squeal is correlated with the magnitude of the positive real eigenvalue, real part. So when the further you go into the right half plane, the louder and more annoying the noises. I'll show you them.
Temperature should be involved. Because
Oh yeah, there are lots of other things involved.
The car is cold.
There are lots of other things involved. There's in this parameter P, there's temperature, there's viscosity, there is the time that you run the car because the stuff is shaved off, and lots of, I'm making it easy here. And you want a efficient method to compute all the eigenvalues with positive real part for the whole parameter set. And why do you want that? You want to use this for model reduction and to find the bifurcation points. And how do you do that? You compute a constant spectral projection of this polynomial eigenvalue problem that captures all the parameters.
I thought you were making this easy.
And then you optimize the device over this model. So these are the two problems. One real-world problem from industry, the other one a future problem, because I think nobody runs adiabatic quantum computing yet, but it's in theoretical physics. But essentially the same problem. You have a parametric eigenvalue problem, and you want to follow a few eigenvectors. So first thing, can we deal with limited accuracy? can we assess the accuracy still if we use inexact Krylov, so with 3 digits or in a tensor format? Can we still do that? Can we assure that we find all the eigenvalues that we want? Can we compute the error bounds, and in which norms should be computed? Can we modify the subspace dimension if necessary, if the things cross? And then can we use adaptivity in the model? And there's just after a long time, finally my student Ute Kandler finished her thesis, which I still have to write the report on, but that deals with these questions. So what is limited memory Arnoldi's method? And we actually, despite the fact that this problem is symmetric, we're using Arnoldi because we have a better hand on understanding than for lunches. So store the matrix operator in lower precision or tensor format, run Arnoldi in the reduced format, and after every step, you chop. After every operation, you chop back to that format. And question, does it really give good results? So what is inexact Arnoldi? It's just standard Arnoldi, but when you do the matrix vector multiplication, where we usually write A times V, you make an error. And that error is the chopping error. Chopping it to low precision or chopping it to the tensor format. Then we do Gram-Schmidt in one or the other way. But we cannot do Gram-Schmidt. So in which way should we implement Gram-Schmidt if we are in such a format? I will have it on the next slide. And then you generate the Hessenberg matrix and the subspace, and then you keep going, and at some stage you stop this and compute the eigenvalues from the small problem as usual. The second is Gram-Schmidt. So if you have standard Gram-Schmidt, you would have that this D matrix there is the identity, because Q transpose Q is the identity. But in this case, we don't have Q transpose Q to be the identity. So we have an extra matrix, and we have to solve a linear system here at every step. Then we do the orthogonalization step, and we make an error because we chop it. Then the norm computation, that is actually something we can do after we chopped it. And then we have the normalization, and we have to update Qt, the inner product, which is supposed to be 0. So Ute Kandler and Christian Schröder worked on this for quite a long time, and it's rather ugly perturbation analysis. But let me give you this theorem here. Is if you take A, CNN, V, a vector of Cn of 2 norm 1, and you compute these perturbed subspaces and the perturbed Hessenberg matrix, then the error that you do is k times epsilon times the error in the computed W vector, and the error for the this is the orthogonalization. That's S was the perturbed normalization, and then the inner product that we get has that bound. Now it's not so easy to understand in such a talk, but let me say if the kappa k is small, then orthonormality is well preserved. Otherwise, you have to add reorthogonalization. So without reorthogonalization, you probably will not get anything at all. So what we get at the end, we do a Wilkinson backward error analysis, and we get that what you compute is the perturbed Arnoldi relation plus an error, and you write this in the typical way as a backward error. And what can you show for the error? If hk and fk satisfy the Arnoldi relation, the approximate one, then what you can do is you can find for a Hermitian bk there exists a Hermitian ek, which you put in the backward error, and we get the usual Arnoldi relation. So we have the usual Arnoldi relation for a perturbed problem. And the question is, we have a freedom in choosing this bk. So how do you map your computed values back to a Hermitian matrix? And we did a lot of analysis here, and the best choice is to take the Hermitian part of the Heisenberg matrix. So we run Arnoldi, we give up the symmetry, and then we map it back to a symmetric matrix. And here's a picture about the loss of orthogonality. So this is classical Gram-Schmidt, this is this compensated Gram-Schmidt, and this is modified Gram-Schmidt. And if you don't do reorthonormalization, that's the bottom curve here, then it will go off. With reorthonormalization, you can fix it at least for the last two. For this compensated and for modified Gram-Schmidt, but not for classical Gram-Schmidt. And without reorthogonalization, we get these backward error bounds. So we can the dashed line is the bounds that we have from this analysis, and the other line is the true error in the cases we know. So we can do that. So we have also implemented that in the so-called tensor train. It's a tensor format. And Ute and Christian did a full backward error analysis, pretty ugly stuff, and got error estimates. And that can be used very nicely in eigenvalue tracing. And let's go back to the parametric model. So how do you deal with this break squeal problem? Well, the first thing you do is companion. Now, if you read the papers by François and others, companion is not always the best, but let's do companion. These are large-scale problems. You get a linear generalized eigenvalue problem. You run shift and Arnoldi method. For this audience, I don't think I have to do that. So you build this Krylov subspace for the matrix W, which is bt omega times a tau, and then you have to solve the system with b tau and run it with a tau. And then you use, for every parameter you generate, the eigenvectors that you're interested in. So you sample the parameter set, you get the eigenvectors that you're interested in, you put them in a big matrix, you run the SVD, and throw the small singular values away. And you choose Q to be the subspace to the big eigenvalues. Now, when we did this, oh, there's an error here. It's not Bach, but Beck. When you do this, you can do the analysis, and you need to use pseudospectral analysis. And we did this for the car industry, and this is the pseudospectrum for a model from a famous German car manufacturer. And this is the level here of 10 to the minus 14. And you can see these results are complete garbage. So we worked on this for a long time, highly sensitive problem because they added stiff springs, and Nick and François have a paper about this. And we made the connections rigid, making the eigenvalues at infinity. That worked it out. And we could solve the sensitivity problem, but we would have to solve the pseudospectral problem to tell them. And here's the last slide in this respect. So we did this for 1,000,000 degree of freedom, and we needed something like 30 eigenvalues to get an approximation for the whole parameter range of size 10 to the minus 6. And I'm not going to talk about this, but I think there's a wonderful new topic, that's dissipative Hamiltonian system, which can bring in the structure in a more nice way, and we don't have good method for that. So I'm stopping here in this respect and move to the conclusions. So eigenvalue problems are still pretty much on the topic. You can use fine mesh and model reduction that usually works, but the numerical linear algebra method are not satisfactory, and this is 60 or 70 years after the problem. We still have trouble with multiple eigenvalues, complex eigenvalues, Jordan blocks. We need limited adaptivity, eigenvalue curves. We have to study nonlinear effects, and I think Jim's heritage is everywhere. Thanks.
Thank you, Volker. Any questions or comments?
There's.
Thanks. I have a question about eigenvectors and break squeal. So as we know, even for a Hermitian problem, when eigenvalues come close together, eigenvectors, because of beating in effect, can localize and get very big effects.
Yeah.
And I'm wondering, is that phenomenon in fact an important part of what makes the break start squealing?
No, it's actually really the effect. It's physically, it means there's a flutter instability. We've heard that from Jim Wilkins. The flutter instability due to when the disk rotates, at a certain clamping pressure, the stuff starts to oscillate, and then it starts to get resonance with the brake pad, and that is the squeal. It's really a resonance phenomenon. So you try to push this in such a way that it doesn't get into the resonance regime. Eugene?
Did you say with classical Gram-Schmidt, even if you reorthogonize, it doesn't work?
Yeah, for these limited accuracy
Okay.
methods.
So that means that with regard to the limited accuracy, the original vectors are highly non-orthonormal.
Yes, the D matrix slowly deviates from the identity matrix, and after a number of steps, the inverse that you have in that algorithm makes a much bigger effect, and if you don't reorthogonalize, this effect will destroy a lot of the accuracy that you can get.
But your other algorithm was being helped by reorthogonalization.
What?
I'm sorry, I thought you had another compensated.
Yeah.
That one improves the accuracy by.
Yeah.
Okay. Why is that?
The reason is because you map the problem to essentially a nearby problem with a Hermitian Hessenberg matrix, or tridiagonal, where you have the control, and that you can control this mapping problem. So it's really a compensation trick. You do the backward error analysis on the small problem yourself, and you do it back to a structured problem. And that is the key understanding behind it.
So that's why you couldn't use householder or given? Some methods that do not depend, where the deviation from orthonormality doesn't depend on the condition number of the original vectors?
Exactly.
I see.
Okay, I think that's a good point to move on.